Welcome to the deep dive. Today we're getting into the sources behind Charles Kaw's Nobel Prize-winning work on fiber optics.
Mm.
And our mission really is to figure out how he solved this material problem that everyone else thought was completely insurmountable.
It's such a great story of one person's insight just completely overturning the consensus. And to get a feel for it, you have to start with his 2009 Nobel Lecture.
Right.
He talks about getting these two letters in the 1970s. One accused him of releasing an evil genie,
Wow.
and the other was from a farmer in China just asking for a way to send a message to his wife who was far away.
That's a huge range,
Yeah.
the mythical and the deeply personal. But before all that, in the early 60s, communication was a totally different world.
Oh, completely. At places like STL, where Kyle worked, it was all about millimeter wave transmission, around 35, maybe 70 gigahertz.
And then the laser shows up.
Exactly. And suddenly you have this light source at 3,000 terahertz. The potential capacity was something like 100,000 times greater than microwaves, but actually sending that light anywhere, it was a disaster.
The sources are pretty clear on why. Trying to send it through the air, the signal just flickered out.
Mm-hmm.
So Bell Labs, others, they spent years on these really complicated pipes and gas lenses to guide the light.
A total dead end.
So, okay, if all that elaborate stuff wasn't working, why didn't anyone just try using glass? I mean, it's transparent, it's everywhere.
Well, that's the genius of Cal. The entire scientific community was obsessed with the mechanics of guiding the wave. The lenses, the pipes.
The container.
Right. Cal was the one who shifted focus to the material itself. He looked at silica glass, which is basically just purified sand. The problem was the best glass they had back then had a loss of 200 dBs per kilometer.
Which means the light could only travel a few meters, right?
A few meters at best. But here was his insight. He said, wait a minute. The problem isn't the glass, it's the impurities in the glass. Literally. Tiny bits of transition metals. Iron, copper, manganese. And this led to his incredible prediction in his 1966 paper. He argued the intrinsic loss of pure glass, what we call Rayleigh scattering, could be as low as 1 dB per kilometer.
And he didn't just point out the problem, he gave them a target. A real number to shoot for.
He did. He calculated that if you could get the iron concentration down to just 1 part per million, you'd hit a practical target of 20 dB per kilometer. That would be good enough.
And how did that go over?
People were hugely skeptical. The sources say British Telecom was somewhat scathing, and even Bell Labs didn't take him seriously for years.
Well, you can kind of see why. How do you even prove that a kilometer of this stuff would work when you can only make a tiny piece in the lab?
It was so painstaking. His team had to invent this hypersensitive double-beam spectrophotometer.
And that was just to measure the loss in these little 20-centimeter samples.
That's right. They were looking for these minuscule differences, and then they had their eureka moment. They tested a sample of infrasil glass from a company called SCHOTT. It measured an attenuation as low as 5 dBs per kilometer.
Wow. So that was it, the proof.
That was the single measurement that proved the theory from 1966 was right, and it just unleashed this global race.
And Corning jumped on it immediately.
They did. By 1970, they hit 17 dB per kilometer. By 72, they were down to 4 dB kilometer. The material problem was solved. And, well, the world was never the same.
It's staggering. Since that first system in 1976, the capacity has gone up 1,000,000 times over. It's the literal foundation of the World Wide Web.
He really did shrink the world. There's that great story that he got the news about his Nobel Prize over a phone call.
Carried on optical fibers.
Carried on the fibers he pioneered.
Yeah.
And then congratulations from Asia came pouring in just minutes later.
You know, what's so fascinating is that even after seeing all this happen, he still felt we were just at the beginning.
Absolutely. He pointed out that the bandwidth we've achieved is already 100,000 times higher than even his own most optimistic early predictions.
And his final thought on it is really something to chew on. He said the unused amount of bandwidth beckons and tempts.
It's a profound idea, isn't it? The man who basically invented the information superhighway believed we've only just built the on-ramp.
So the next time you're streaming something, just remember, the revolution that started with purified sand might still be accelerating.